In this example problem, we have an emergency braking system that is designed for a possible runaway futuristic personal shuttle, involving the shuttle coming to a final stop against a horizontal spring on a horizontal frictionless surface. The shuttle has a mass of 500 kilograms and an initial velocity of 4 meters per second. And it must come to a stop where the acceleration it experiences as it's decelerating needs to be less than 3g, so 3 times 9.8. We want to know what the spring constant has to be in order to constrain the maximum acceleration to 3g. Alright, so we have a spring, which indicates that we probably should use conservation of energy, especially since we have a single object that we're taking from being in motion to stopping. So we look at, initially, we have a whole bunch of different types of energy. So we have kinetic, potential energy, gravitational, potential energy due to the spring. We have work non-conservative, and then we have kinetic energy final, plus potential energy gravitational final, plus potential energy of the spring final. Alright, so when we look at this, we have an initial velocity, so that tells us we do have kinetic energy initial. Now we're on a horizontal surface, and we can define the horizontal surface of the horizontal surface to be y equals 0. So that means initially we're at y equals 0 and final we're at y equals 0. And then when we look at the spring potential energy, the spring is initially relaxed because you're going to run into it and compress it. So that means when it has velocity, you have no spring potential energy because the spring is relaxed until you hit it. So this is going to be 0. And then we're on a frictionless surface, so work non-conservative is 0. And you're going to come to a stop, which means kinetic energy final is 0. So we're left with the idea that we're going to transfer our initial kinetic energy to the spring. And it's going to become fully compressed. So you could transfer all of your kinetic energy to the spring. So that's what I'm starting with up here, the idea that we have our kinetic energy, which is 1/2 mass times velocity squared, and that's going to equal the spring potential energy. So 1/2 times spring constant times the compression squared. Now as we go through this, we're run into a problem. We have the mass of the object that is going to be compressing the spring. We have its initial velocity, so we can calculate the kinetic energy. But when we get over here to the spring potential energy side, we don't have the spring constant and we don't have how far it's going to be compressed. So we're trying to find the spring constant, so we need to get rid of the compression amount. And we're going to find that compression amount, or at least make a substitution for that compression amount, by summing forces. So we have our wall with our spring sticking out, and the cart is going to hit this spring and compress it. So imagine I can actually draw, and this is sitting on that horizontal surface. If you look in the x direction, because we're not worried about the y direction, because the spring is horizontal and not vertical, the only force acting on the spring the only force acting on the cart as it comes to a stop is the spring force. So the spring force is the only force acting in the x direction, because we said it was a frictionless surface. And nobody's pushing on the cart. There's no ropes attached to the cart. So all we're worried about is the spring force. Now, normally we run into an issue here because when we replace it with k times x, the more the spring is compressed, the more force it's going to apply to the cart. But all we're trying to do is find a spring constant where no matter how much we increase x, the acceleration never gets over a specific value. So we're trying to say whenever this is at maximum compression, it's equal to the maximum amount of deceleration we want. And then the system comes to a stop. So it never actually manages to get over the deceleration that would be harmful. Of course, this only works as long as you continue to use the same vehicle or cart to transport the person. Once the mass gets larger, that's going to affect the system. So it's set up for this specific system. Alright, so what I've done up here is rearrange this relationship for the compression and subbed it in for the compression here. I've now distributed my square here, and that's, you notice there's no square here, but that gets canceled. One of them gets canceled out by this here. In addition, I've canceled out the 1/2 on both sides. Alright, now I algebraically rearrange the relationship to solve for k, and I plug in the mass 3 times the g, which is going to be our deceleration, and then our initial velocity provided in the problem, the 4 meters per second. And that gets me a spring constant that is 2.7 times 10 to the 4 newtons per meter, which is a large spring constant, but not an unreasonable spring constant for something you would use as part of a braking system.